All right, nerds. Rare occasion re-recording this year, right? But I did discover today that I needed some more videos. So, the beginning of 2.7. I don't think I have any of 2.7. Yeah, I think I'm missing all of it. So anyway, well, we'll see. So the beginning and a bit past the middle of lesson 2.7. Unit 2.7 is compositions of functions. That means plugging one function into another function to build a third function. It was this great Pimp My Ride composition of functions meme that used to be pretty relevant, but now none of you really remembers or even knows what that is. Unfortunately, you missed out. But anyway, if I have time after I get where I need to get, I'll show you. So I already told you. Compositions means plugging one function into another function to end up with a third function. This little graphic right here is showing you like, hey, look, you could start with x, and you could take that x and you could plug it into g of x. Now, g of x would give you a y value. You could then take that y value and if you wanted to, plug it in as the input of f of x. And it would have been the same as doing f of g of x. Which brings me to what that little O thing is. It's of. It means of. It's a little composition operation. It's a circle, not a decimal point, not a multiplication dot. It's a circle. So these two things mean exactly the same thing. They both say, take whatever g of x is and plug it into f of x. F of g of x, fog x. I prefer writing it this way, because this way really shows you that g of x is now the input. F, its output values are what you get when you plug in x into g and then take that number, plug it into f. So it's function in a function. It is important to understand the notation conventions for compositions of functions. Why, Mr. M? Because this does not mean f times g of x. This does not mean f times g of x. And that's often what I see go wrong, is that students think that they're doing some kind of multiplication either here or here. It's not multiplication. It's a function, and the input is being manipulated. Also, another way that I have seen this go wrong, some students will actually do the composition correct and then think they're supposed to multiply their composition by x. No. F of g is the name of the function, x is its inputs. That's what that says. Now, a lot of times we'll rename f of g, like h or something like that. But just know that there is no multiplication going on here. Okay? The little O means of. And just so you know, if you were wondering, generally, order matters. Are there some exceptions where order doesn't matter? Yes, there are. But for the most part, you're going to find out that f of g of x is not the same as g of f of x. To prove that point, we have example number 1. Using these functions, f and g, find f of g of x, find g of f of x, and then determine whether or not compositions of functions are commutative. Commutative means order doesn't matter. Like addition. Addition is commutative because 2 plus 5 is equal to 5 plus 2. Multiplication is commutative. 6 times 3 is the same as 3 times 6. This is going to demonstrate that compositions in general are not commutative, because we're about to see that these two things are not the same. I like to color code compositions. 1, because it's fun, and 2, because I think it really helps you see what was the input, what was the output. So anytime I need to use f of x, I'll write in blue. And anytime I need to get g of x, I'll write in red. And anytime I blend them, I'll write in purple. Because red and blue give me purple. Okay. The first one says f of g of x. F of g of x. If I had said f of 5, you would have plugged 5 into f of x. I'm not saying f of 5, I'm saying f of g of x. That means everywhere that f of x had an x, my job is to have a set of parentheses, and I'll put the red g of x in those parentheses. Here's everything that f of x had. Where there used to be an x, there is now a set of parentheses, because that is where I'm dropping in what g of x equals. Distributing the 3 is going to give me 12 minus 3x, and there's still this minus 5x hanging out at the end. So f of g of x will clean up to negative 3x plus 7. Now I have to compose them in the opposite order, g of f of x. That means wherever g had an x, I will open a set of red parentheses, and that's why I'll drop in the blue information, which is f of x. 4 minus, and there used to be an x here. And this is where I'm putting 3x minus 5. Please remember that that minus sign that sits in front of these parentheses is acting as a -1 multiplier, almost as if you're distributing the minus sign. 4 minus 3x plus 5 cleans up to negative 3x plus 9. So as you can see, f of g of x is not equal to g of f of x. Compositions of functions is not commutative. Are there special times when the compositions equal each other? Yes, there are special times. And we'll get to that in a later section, not in this section. Okay? Is everybody calm, cool, and collected on how I composed these two functions? No questions about it? Alrighty. Yes, Chris, what's up?
Could you say again where, when you're plugging in for like g of x, where the x disappears?
So x didn't so much disappear when I was plugging in this red stuff or when I was plugging in this blue stuff. Let's say for a minute, let's say I asked you to find g of 6. If I had said g of 6, then what you would have done is 4 minus 6, right? So what we've done is we've said g of f of x. So imagine it says 4 minus f of x. And that is f of x. So we're plugging in kind of like transformations. We're replacing x with something new. We're replacing our input. Is it better? Okay. Yes, ma'am?
Does commutative mean equal to each other?
Commutative means order doesn't matter.
Oh, okay.
So like I said, addition is commutative and multiplication are commutative, but subtraction's not and division's not.
So is it asking,
It's just saying,
does it matter?
it says, can you determine whether compositions are commutative? They're not, because order clearly changed the answer. That's basically what we're saying. Because their order gave us different answers, we know compositions are not commutative. On this back side, for example 2, we actually have 4 different examples. We have 3 functions, an f, a g, and an h. I'll color code these as well. Unfortunately, I don't have enough pen colors to blend my colors very well. So, I won't be blending anymore because, red and green makes brown. And blue and green makes blue-green. So it doesn't really work out very well. But I'll still do f of x being blue. I'll still do g of x being red. And I'll do h of x being green. Now, what these 4 examples have asked us to do is compose the 2 functions that it's showing us. And then, for funsies, find the domain of the new function. Hopefully you remember doing that in Algebra 2. F of g of x. F of g of x. So where my blue function had an x, instead I have a set of parentheses. And within those parentheses goes my red function. There it is. Like I said, I'm not going to blend colors here because I'm already using 3 different, and these 2 are the only 2 I have that blend nicely. So I'll just keep writing it in blue. Squaring a fraction is the same as squaring the top and squaring the bottom, so you get this. Boop. And as far as multiplication goes to a fraction, this is a whole number, just gets multiplied to the top. There is f of g of x. But what is its domain is the question. What we have here are rational functions, and the only rule that we have about rational functions is you can't divide by 0. And if you do try to divide by 0, what you have found is a vertical asymptote. Unless, of course, it cancels out, then you have a hole in the graph. But you can see nothing's canceling out. Hopefully, you can tell me the x value that would have made me divide by 0, though. -2. That means x can't be -2. X can be any number except for -2. So that would mean that our domain is everything except for -2. So I'll use interval notation, -infinity to -2. And that's going to have a parenthesis on it because we're avoiding that number. We'll hop over it with the union symbol, pick back up on the other side of it, and head towards positive infinity. There it is. That says everything except for -2. For part B, all we have to do is compose the functions in the opposite order. Take the blue one and plug it into the red one. That means wherever the red function had an x, that's where you're going to drop in your blue function, and you really should be in the habit of substituting with parentheses, even if they actually don't make a difference, like in this question. So the parentheses didn't have a job really in this question, and that's okay. You know, we use a parentheses like you use a seatbelt. You don't put it on because you know you're going to get in a car accident. You put it on in case you get in a car accident. And if you got home safely and you go, wow, I never need my seatbelt that whole drive. Well, whatever, it's just a little insurance policy. Parentheses are the same way. I'm going to go ahead and drop them because I can see they're doing nothing. And just like example A, we have a rational function. You are not allowed to divide by 0. I guess the question becomes, is it possible for this quadratic to equal 0? We know how we'd find out. Set it equal to 0 and factoring, my favorite F word. That's not true. That's like my second or third favorite F word. Anyway, factoring, okay? Yes, this factors. Yes, there are two numbers that multiply to 2 that add to -3. Those two numbers are -2 and -1. And since my denominator is in factored form, I can see there's actually two numbers that would have made the bottom equal 0. I can see x can't be 1 and x cannot be 2 either. So then how would we write that in interval notation? Very simple. Union symbols around the 1 and around the 2. So we have two unions. Everything to the left of x equals 1, hop over 1 with a union symbol. Everything from 1 to 2, hop over 2 with the union symbol. Everything after 2. And there it is. The lesson's actually about the composition stuff. The domain finding that's like icing on the cake. All right. F of h. F of h is an interesting one. I do something very similar to it in my Algebra 2 class. Let's see. F of h of x, like that. Where the blue one has an x, I want you to put a set of parentheses. And we're going to fill those parentheses with the green structure, which is square root x. You determine domain before any symbols simplify things. What do I mean by that? Well, what if, for the moment, we had said that was our whole composition? If that was the whole composition, Squares and square roots cancel each other. So again, if this part didn't exist, then what we would say is y equals x. And that seems like its domain would be all real numbers, right? But it's not. And the reason why is because you have prior knowledge. It's kind of like how deleted points, deleted, what are those things called? Removable discontinuities, holes in the graph. You have prior knowledge. Ooh, that was an x that I wasn't allowed to use, and that's why I have to mention it as a hole in the graph. You have prior knowledge before you simplify this, and you know that you cannot take the square root of a negative number in the real number system. So this thing's domain, even though this square root and this square cancel each other, is still x is greater than or equal to 0. Of course, we have that going on, so it cleans up to this. And this part right here makes it obvious that the domain is x is greater than or equal to 0. Because you can take the square root of 0. I just wanted to make a point about, well, what if it wasn't there? And the last one, h of f. H was green. Square root of this blue stuff. I hope you'll forgive me for not using the parentheses because I could see they had absolutely no purpose. So I went ahead and skipped over writing them. I saw they were going to be useless to me. We cannot take the square root of negative numbers in the real number system. We can take the square root of any number greater than or equal to 0 in the real number system. That means the argument of this square root question, the blue part, x squared minus 3x, must be greater than or equal to 0. That's a quadratic inequality. And we solve quadratic inequalities by factoring and using sign diagrams. This is the composition. This right here, this is it. It's finished. Finding its domain is the interesting part. Always start factoring by looking for a GCF. This one happens to have one. That GCF is x. Then you build yourself a x-axis, a sign diagram, and you put the two numbers on it that would have made this thing be equal to 0. That's x equals 0 here, and x equals 3 here. Little sign diagram action for you. Yes, ma'am. I didn't get rid of the square root. What I said was, I know I can't take the square root of anything negative, but I can take the square root of things that are greater than or equal to 0. Because the square root of a negative would have been imaginary. Square root of 0 is 0. The square root of anything positive is something positive. So as long as the blue quadratic produces y values that are 0 or bigger, we're okay. So that's why we're doing that. So we didn't get rid of it. We just said it is what forced this part to happen. Okay. Now we're going to test our zones to look for the signs being positive or negative. Let's grab a number to the left of 0, like -1. You put a -1 right here, you get a negative value. And you put a -1 right there, you get -1 minus 3, which is another negative value. And you're being forced to multiply those two negative values. If you multiply two negative values, you will always get a positive result. This is you multiplying right there. The numbers themselves don't matter. All we care about is, are they positive or negative? That's all we care about. As long as this quadratic is producing positive results, we're in good shape. So this area is one of the areas we were looking for. We found positive values. Take any number between 0 and 3. I don't know, like 1. 1's a great number. Putting a 1 right there gets you a positive number. Putting a 1 right here, 1 minus 3 is a negative number. Now you're looking at the product of a positive and a negative, which all day long will get you a negative value. Oh no, remember, our quadratic cannot have negative values because if it does, we're trying to take the square root of a negative blue number, and that's not allowed. So nothing between 0 and 3 is allowed. Check after 3. Mr. M, don't they always oscillate between back and forth, positive and negative? No. Always check. Always, always, always check. Let's plug in x equals 4 and see what happens. Positive 4. 4 minus 3 is also positive. The product of two positive numbers will be positive every single time you try. Therefore, we found two zones where our blue quadratic would have produced positive values, or 0, which I can take the square root of. So I've got everything to the left of 0, including 0. Because at 0, I'm taking the square root of 0, which is allowed. And then everything to the right of 3, including 3. At x equals 3, once again, I'm taking the square root of 0. So again, finding the domain was actually more fun than actually composing the functions. It's kind of basic. No more domain stuff. Just compositions now. Boop. We're going to use the graph of f and g to evaluate some compositions with some arithmetic. I don't like this style. I prefer to see this as f of g of 3. What I'm going to do is I'm going to figure out what g of 3 equals. So go to your graph for g, go to x equals 3, and then look for your y value. Your y value there is 1. That means instead of writing f of g of 3, I can write f of what g of 3 equals. I can write f of 1. G of 3 equals 1, so I can write f of 1. Now I get to go to graph f, go to x equals 1, track down my y value, and see that it's 2, and boom, there it is. If you have questions about that, please say something to me. Yes, ma'am?
How'd you get g of 3 equals 1?
So I went to the graph of g, and this literally says when x is 3, what is the y value of the graph of g? So I went to here to there. So that y value was 1.
Thank you.
Let's do it again. F of g of 1. I need to know what g of 1 equals. So once again, go to the graph of g, go to x equals 1, track down the y value there. 3. So instead of saying f of g of 1, I can say f of what g of 1 equals. Go to the graph of f, track down x equals 3, look for your y value, 2. They don't get any more difficult than that. I mean, we could have to do a couple things and then multiply, but they don't get any more difficult than that. You should work from your inside out. Always work from the inside out when you're doing these composition evaluations. So g of 4 is going to be the first thing I want to look for. Switch colors. Let's get g of 4. G of x equals 4. Oh, there it is. It's 0. G of 4 is 0. And f of 1, I already know f of 1. It's right here. So we already know that. This question actually then says f of 0, because that's what g of 4 equals, times g of 2, because that's what f of 1 equals. And then we can come to the graph of f, see x equals 0 is right here, track it all the way up to the y value of 4. Then I can go to graph of g to x equals 2. Y value happens to also be 2. and get 8 as my result. I like evaluating compositions. It feels like a scavenger hunt. Yes? You sure? Okay. That's another good color. I haven't used purple yet in this question, so I'll track down purple. A little bit of free money here. This denominator, f of g of 3, that's this question. F of g of 3 is right here. So this denominator is actually 2. We already know that. It's right there. F of g of 3, 2. So we just need to know what f of negative 1 is, because we know the denominator is 2. So go to function f, go to x equals negative 1, track it up to a y value of 6. I get 6 over 2, which is 3. Example E is free money. We already know what f of g of 4 is. It's right here. This is f of g of 4. It is 4. Ta-da! It's free. It's right there. There's f of g of 4. Done. Don't even have to work for that one. We already did it. But we haven't done g of f of 2 yet, so let's go ahead and handle that one. Restarting back to green. Let's see. This is, wait, messed up my own pattern. G of f of 2. Let's see what f of 2 equals. So go to function f, go to x equals 2. See your y value there is a 0. Instead of saying g of f of 2, say g of what f of 2 equals, which is 0. G of 0. Go to function g, x equals 0. Track it up to the y value of 4. Compositions are fun. I think they're fun. Anything in math that can be done can be undone. So if I could put two functions together, I could take them apart. Decomposing functions. That just means what was plugged into something else. Pretend your function is h of x. What we're trying to do is figure out how could I represent this as f of g of x. When it's written that way, you can see that g of x is on the inside. And you can see f of x is the outside. So take a peekaboo here at this quadratic, and then tell me what function appears to be inside something else. What appears to be inside something else? X plus 3, yeah. X plus 3 happens to be inside of a squared structure. That means my outside is simply the squared structure. X squared. We have decomposed. And just so you know, there's an infinite number of correct ways to decompose functions. Again, what we're saying is, if we were to take this x plus 3 and put it right here with the set of parentheses, we would have f of g of x, which is h of x. We just said, what was plugged into something else? X plus 3 is plugged into something else, and that something else clearly squared x plus 3. And there it is. For this fraction, someone other than Gavin, what looks like it got plugged into something else? X minus 5 is the easiest way to handle this. Yes. So I would say that the bottom of the fraction is what got plugged in. Plugged into what? Plugged into a fraction. Oh. There's a 1 on top of that fraction, and x minus 5 is the entire bottom, so I must have replaced an x with an x minus 5. If you replace this x with this red x minus 5, you get that. This one's really easy to see what is inside. I hope. London, you tried to help me with B. What's inside? What got plugged in this one?
X plus 2.
Yeah, x plus 2. Again, there's an infinite number of correct ways of doing it. That's the easy one. So x plus 2 got plugged into, looks like square root of something. I think we're kind of getting there, right? I hope it's really obvious what's going on here. Hey, what does this look like, though? I used to have x's here, but now instead I have x minus 2's. What does that look like? Right, but what is it? We've done this kind of math before where x got replaced with x minus 2. Looks to me like it says shift right 2.
All transformations.
It's transformations. You see, all transformations are compositions of functions. This is just transformations. Now, I've already said it a couple different times, but there's an infinite number of ways to decompose functions. There's no such thing as what is the decomposition. It's always what is a decomposition. There's no such thing as the best either, no. Now, there could be a multiple choice question. It says, which of these is a valid decomposition, which you might remember from my tests last year. Yes. We did it. Yep. So this example says, hey, decompose this in 2 different ways. Let's do the low-hanging fruit, the easy way, the same way we did it here for C, where we could just say that the entire inside is g of x. And that it has been simply plugged into a square root bar. That's the easiest way. Could someone give me another way? X squared. Oh, yeah, wow. You're absolutely correct, but wow, you worked way too hard for that. So what he said was, you said,
So g of x, f of x is
okay, square root of 3x?
yeah.
Yeah. Hold on, I'm trying to figure out what color I'm supposed to write that in. You said, I'm going to write it. It's correct. It's working really hard, but we'll do it. You said square root of 3x. So then what are you plugging into that to make that work out? X squared plus 1/3 would do it. Here's why. Remember, you're supposed to substitute with parentheses, right? If you wrap this in parentheses and distribute a 3 to this, you will get 3x squared plus 1. An even easier way of doing it, though, would have just called this square root of x plus 1 and just said this was 3x squared. And Gavin, you had another way?
I was just going to do the inside would be 3x, the outside would be the square root of x squared.
Now if we did 3x and the square root of x squared plus 1, you'd actually have to square the 3 and the x, and you would have gotten 9x squared. So you could do that as long as you also included some more stuff underneath the radical. And that's why I said there's an infinite number of correct ways. Max?
Would the square root of 3x plus 1 and the g of x would be x squared?
You could also do that, yeah, he said square root of 3x plus 1, and then just say that g of x was x squared. Lots of different ways to do it, right? On your test review that I'm making, I gave you a question, and I just said, come up with as many ways as you can. Just be a little creative. Okay? So how about some interpretations? Jim plants wheat on his farm in Kansas. The function w of a gives the amount of wheat, capital W, in bushels that he expects to harvest if he plants wheat on A acres of land. So capital W is bushels of wheat, lowercase a is acres of land. Just like any good farmer, when this wheat is harvested, Jim's trying to make some money, and he calculates his money, capital M, in dollars that he will earn by selling his W bushels of wheat using the function M of W. So capital M is money in dollars, where W is still wheat bushels. Cool beans? Yes, fantastic. So here we have, explain the meaning of W of 5 equals 275. So you ask yourself, what is the input of function W? Well, the input of function W is A. That means 5 is A. A is acres. The output of function W is bushels of wheat. So this says 5 acres of land produces 275 bushels of wheat. The next one is using function M. M for money. The input for M is wheat bushels. The output is dollars. So this is 65 bushels of wheat. We'll earn $550. Forgot to write earn. But the last one's a composition. Max? Sure, you can try it. Go for it.
When the amount of bushels is 4 acres worth,
Uh-huh.
you will earn $2,100.
Yeah, so what he says is, I'm just going to clean it up a little bit for the video, but he said 4 acres of land is going to produce wheat that will sell for $2,100. Yep, there it is. So 4 acres of land produces wheat, I'm going to say worth $2,100. Something like that. Good deal. Now, that is all of 7A, but we do have to move on to 7B and get a start on it just to ensure that I can finish the lesson in tomorrow's short class period. Okay? So we flip it over and we do more compositions. Only this time, instead of a graph, we have a table. The math isn't any different though. Work your way from the inside out. So we figure out what G of 2 is, figure out what H of 0 is. Let's see. G of 2. So go to G of x, then track down x equals 2. Boop, it's right there, -3. And H of 0 is also on the inside. Function H, x equals 0, gets me a value of 3. This question actually says 2 times f of -3 plus 3 times g of 3. So that is going to give me 2 times, let's see what f of -3 equals. Go to function f, track down x equals -3, bloop, right there, -4. And then 3 times, go to function g, and then track down x equals 3, way over here, 2. So what is that? -8 plus 6, -2. I love compositions. Told you, it feels like a scavenger hunt. Or like a pirate map where every clue you find just leads you to another clue. I like it. How about g of -2? What? Anyway, g of negative 2. Go to function g, track down x equals negative 2, negative 1. Let's figure out what g of positive 2 is, because that's also on the inside. Function g, x equals 2. So we have h of negative 1 times f of negative 3. Function h, x equals 1, 2. Function f, x equals negative 3, negative 4. And that's it for that one. The last one, example C, and we're done for the day. Is that it? Yes? Oh, yeah?
Isn't it h of negative 1.5?
H of negative 1. What did I write? Oh, my goodness. Yeah, where did I get that from? Oh, I went to h of positive 1, didn't I? Man. Poo. Let's try it again. H of negative 1 is 1.5. Shucks. Yep. And 1.5 times negative 4 is negative 6. Dagnabbit. I was doing so well. Yep. This last example for today says k of x, oh, so we have another function now, the absolute value of 3x minus 4. And we want to know when will k of x be equal to f of g of 0. So the first thing we need to do is evaluate f of g of 0. Well, what is g of 0? Let's start there. So go to function g, x equals 0 to 1. So this actually says f of 1. Function f, x equals 1, 4. What we're trying to figure out is where the absolute value of 3x minus 4 equals 4. We're done with that table now. And if you can remember all the way back to Algebra 1 days, when you're solving an absolute value equation, you have a positive case and a negative case. The positive case says drop the bars and solve for x. The negative case says drop the bars and switch the sign and solve for x. And that's it. So we're going to add 4 to both sides and divide by 3. Or add 4 to both sides and divide by 3. Those are your two results. And that's going to do it for today. Yay! Appreciate you, nerds.